Imagine you are running an A/B test. Your experiment is supposed to run for 2 weeks, but after only 3 days, you open dashboard. Treatment group is winning. P-value is below 0.05. Everyone celebrates. New feature is launched. Months later, sales return exactly where they started. Improvement completely disappears. So what happened? Was the statistical test wrong? No. Was the software broken? No. Mistake happened long before decision. Because every time you looked at results, you unknowingly increased chance of fooling yourself. And this surprisingly common mistake has a name, picking problem. It quietly creates false discoveries. It wastes engineering efforts. It ships features that never actually work. Welcome back to Shital's Data Desk. I'm Shital and in this video we will cover below topics one by one. By the end of this video, you will understand why one innocent dashboard check can completely invalidate an experiment and more importantly, how to prevent it. So, let's begin with basics. What exactly is peaking? Peaking simply means checking experiment results before experiment reaches its planned stopping point. For example, suppose your experiment was designed to collect 20,000 users. But after only 4,000 users, you check dashboard, waiting for statistical significance to appear. If result looks significant, you stop. If not, you continue. That is peaking. Notice something important. Simply viewing dashboard is not the real problem. Problem begins when decision depends on what you saw. Because statistical tests assume something very specific. They assume sample size was fixed before experiment began. Once that assumption changes, math changes too. But why does looking more often change the probability of making mistakes? Answer is surprisingly simple. Imagine buying a single lottery ticket. Your chance of winning is tiny. Now imagine buying 100 lottery tickets. Your overall chance of winning becomes much larger. Not because lottery changed, but because you gave yourself many more opportunities to get lucky. Picking works exactly the same way. Every time you check your experiment, you perform another statistical test. And every new test gives randomness another opportunity to produce statistically significant result, even if no real effect exists. Now let's connect this to something we have seen before. When we chose alpha equals to 0.05, we are accepting 5% chance of false positive. But there is an important assumption behind that number. It applies to one planned analysis, not 10, not 20, and certainly not checking dashboard every single day. Suppose you look at results every morning. Each look is another opportunity for random fluctuations to cross the significance threshold. As those opportunities accumulate, probability of declaring false winner also increases. This phenomenon is called alpha inflation. Although every individual test still uses alpha equals to 0.05, the experiment as a whole no longer has 5% false positive rate. It may become 10%, 15%, 20%, or even higher. Without realizing it, you have quietly changed statistical rules of experiment. Repeated checking becomes especially dangerous when it starts influencing our decisions. And that brings us to optional stopping. Stopping an experiment early simply because data looks favorable is called optional stopping. Instead of deciding sample size before collecting data, stopping point depends on results themselves. And this creates bias. Successful looking experiments end early. Unsuccessful experiments continue. Over time, this tends to exaggerate observed effect sizes. Many published scientific studies suffered from this exact problem. Researchers unknowingly stopped collecting data once significance appeared. Reported improvements looked much larger than reality. This became one of the contributors to replication crisis. Optional stopping doesn't just break statistical assumption. It also creates very real business problems. Because every false discovery eventually becomes bad business decision. Cost of picking is not just statistical, it is financial also. False discoveries mean shipping bad features, rolling back deployments, wasting engineering time, misleading executives, making poor product decisions. Some companies have spent millions building features that appeared successful during experiments, only to discover improvement completely vanished after launch. Good experimentation protects businesses from expensive illusions. Fortunately, modern statistics does not simply tell us to stop looking. Instead, it provides methods that allow us to monitor experiments safely. Modern statistics offer smarter solution. Instead of pretending experiments will not be monitored, it designs tests that allow monitoring safely. These methods are called sequential tests. Unlike classical hypothesis testing, sequential methods are designed for interim analysis. They adjust decision thresholds accordingly. Imagine monitoring an experiment every day. Instead of using same significance threshold each time, sequential testing adjusts rules so that repeated looks remain statistically valid. Examples: sequential probability ratio test, group sequential designs, always valid p-values. These techniques preserve statistical validity while still allowing early stopping. If evidence becomes overwhelming, experiment may end early. If evidence remains weak, experiment continues. This allows organizations to save time without sacrificing statistical rigor. Sequential testing is one solution, but there is another powerful approach within classical statistics. Instead of changing when we analyze data, we change how much statistical evidence we require at each look. Instead of using full alpha at every interim analysis, we divide it across multiple looks. This idea is called alpha spending. Think of alpha like a budget. Suppose your total alpha budget is 0.05. Every interim analysis spends small portion of that budget. Early analysis use stricter significance threshold. Later analysis receive more of remaining alpha. Popular approaches include O'Brien-Fleming boundaries, Pocock boundaries. Goal remains same. Protect overall false positive rate, even while looking at data multiple times. Everything we have discussed so far belongs to classical statistics. But there's another statistical framework that approaches this problem very differently. Bayesian statistics approaches problem differently. Instead of asking, how surprising is this data assuming no effect, Bayesian method estimate how strongly data supports different hypotheses. Because Bayesian inference continuously updates beliefs as new data arrives, repeated monitoring is generally much more natural. Many Bayesian methods allow continuous observation without same alpha inflation issue faced by classical hypothesis testing. That is because Bayesian inference does not rely on fixed horizon p-value in same way classical hypothesis testing does. However, Bayesian methods require different assumptions, different interpretation, and different decision rules. Neither approach is universally superior. They simply answer different statistical questions. That is why many modern experimentation platforms now offer both classical and Bayesian approaches. Whether you use classical methods or Bayesian methods, most picking problems don't happen because mathematics is wrong. They happen because people make predictable mistakes. Mistake 1: checking significance every day. Mistake 2: stopping the moment p becomes less than 0.05. Mistake 3: extending experiments only when results are insignificant. Mistake 4: running multiple experiments and only reporting successful ones. Mistake 5. Ignoring original experiment plan. All of these increases false discoveries. Not because statistical software is wrong, but because assumptions behind software were violated. Fortunately, avoiding these mistakes is much easier than fixing them afterward. So let's look at the practices followed by experienced experimenters. Before starting an experiment, decide sample size, experiment duration, primary metric, significance level, stopping rule, monitoring plan. Write this down before collecting any data. If early stopping is necessary, use proper sequential testing methods. Monitor experiment health, not statistical significance. And once experiment reaches its planned endpoint, perform exactly analysis you planned from the beginning. Good experimentation is disciplined experimentation. And all of these best practices point toward one bigger lesson. Picking problem teaches us something much bigger than hypothesis testing. Statistics is not just about calculations, it is about discipline. Perfectly designed experiment can still produce misleading conclusions if we ignore rules halfway through. Every additional look gives randomness another chance to fool us. That is why great experimenters don't simply ask, is the result significant today? They ask, did we follow plan we committed to before experiment began? Because trustworthy experiments are not built on exciting dashboards. They are built on disciplined decisions. And sometimes hardest part of experimentation is not collecting more data. It is resisting temptation to make decision before experiment is truly finished. If you found this video helpful, don't forget to like, share and subscribe to Shital's Data Desk. Thanks for watching and I'll see you in next video.